This is the set of video notes for chapter 16, pretty much all in one capsule, a fairly short chapter. And I'm going to start out talking about reaction rates. The chapter is about reactions and reaction rates and some of the supporting information. Reaction rate is a lot like the speed on your car. You go fast, you go slow. Speedometer kind of tells you what you're doing, but you can view it. You could be in it and see you're going fast or slow. Well, it's the same thing with reactions. You know, there are reactions that you could see happen, that happen fairly fast. There are some other reactions, some of the ones we've done in class, that you could see that happen pretty fast. And some of them really happen fast. So it's important for you to know how fast a reaction is going to occur or be able to predict that. And then there's some that happen slow. So we're not going to hang around to watch this, but this is a piece of copper that's oxidizing, and we call that corrosion. So we're going to find a little bit more out about reactions and reaction rates. Start out by covering some groundwork and some definitions. Reaction rate, what is it? Well, it is the change in reactants per unit of time. Now, you say, well, what about products? Well, think about an hourglass. As the sand from an hourglass drops from the top, it drops into the bottom. If you know how fast the sand's dropping from the top, you know also how fast it's appearing in the bottom. So, if you know one, you know the other. That's why we're going to deal with the reactants in determining our reaction rate. That's kind of the standard. The reaction rate is then defined equation-wise as it's the number of reactants changing per second per unit of time. We've got several units that we use. When you're driving, you know you use miles per hour, or depending where you are, it might be kilometers per hour. But we use in chemistry, we use molarities per second or moles per liter seconds, and in some cases moles per second. So those are some actual units that we use for reaction rate. The whole thing about reactions is based upon a theory called collision theory. And the idea of collision theory is that you have to have collisions between reactants for them to react. And the more collisions you have, the more reactions. Of course, the collisions have to be with enough force in order to make the reaction occur. We'll look at some factors that control reaction rates, and it's just a matter of, do they speed up collisions? If they have more collisions, more reaction rates. Things like higher temperature. Well, you're moving faster, more reactions. Once reacting particles collide, and they actually do have collisions, they form a complex that we call the activated complex. It's not reactants, it's not products, it's kind of a morph of reactant and product while they're figuring out what they're going to do to become a product. Another term for this is transition state, and we'll use both of those, so you should know both of those terms. In order for a reaction to happen, we actually have to do something in most cases to make it happen. And it may be as little as just raising the temperature, but it doesn't just happen automatically. There's something that kicks it off. We call this activation energy. And on our energy diagrams that we draw during this chapter, it'll be the hump, or usually there's an arrow up under the hump that indicates how much energy is in that hump. That's the activation energy that gets us started. Lighting a fire in your fireplace, lighting the match is the activation energy. After that, it usually goes on its own if you're lucky. So down at the bottom of this page, this next page, there are some energy diagrams, and if you could look over that, be a good idea for you to be able to draw those. You'll be drawing some of those on the review, also on the quiz and test. Notice that we have everything labeled there. The axes are labeled. Energy is the y-axis, and time is really the x-axis. We could call that reaction progress. So as you look at this, notice that the first reactant has, or the first diagram has reactants high, products low. This is what we referred to in last chapter as a spontaneous reaction. Whenever you go from a high energy to low, it's like pushing something downhill. It's going to happen. All you got to do is give it a shove. The second one, the products are higher. So that means that it's not spontaneous. And if you're trying to determine from a diagram, spontaneous or not, look at the products and reactants. If the products are higher, not spontaneous. And then finally, the third one, this is a complex reaction. We're going to talk about complex reactions. And when it comes down to representing these, we're going to talk about reaction mechanisms. And that can either be a picture or a series of reactions in a summation. Either one of those are reaction mechanisms. That's a later page. Notice that there's two humps, which means that there are two elementary reactions in the complex reactions. Kind of like there's two steps, like tying your shoes. You know, one is putting them on and the other is tying the strings. So there's two steps to this reaction, two humps. And, you know, just to kind of discuss a little further on this, the first reaction, first elementary reaction, is a slow one because it's a tall hump. The second one has a leading edge that's shorter than the leading edge on the first. So it would be the faster reaction. So look at the leading edge, the front edge, and when you see the front edge is taller, not just the total height, because the second one's higher in total height, but its front edge is shorter. So it's a shorter hill. Think of yourself running over the front edge of that hill. First one you would run slower, it would take you more time. And notice that the products are lower here, so this is the overall complex reaction is spontaneous, even though the first elementary reaction is not. When you make energy diagrams, make sure you label all the parts. Anytime you're asked to label, that would be the transition state or activated complex on top. Notice that's on top. The activation energy, which is the height of the hump, the reactants, the products, and then, of course, label the axes. Y-axis energy, x-axis would be time or reaction progress. We talked about spontaneity already. Remember that a negative delta G, meaning you've lost energy, is spontaneous. If the products are lower in energy, obviously you've lost some energy. Spontaneous. There's 6 factors that we're going to list that control reaction progress or reaction rates, and I'd like for you not only to know these, but know what effect they have and which way. Do they increase the reaction rate? Do they decrease the reaction rate? First of all is the nature of the reactants, and this one's a little bit different than the others. Obviously, if you have two reactants that won't mix, like oil and water, they're not going to collide very much, and that will mean that they're not going to have many reactions, maybe a few right where they have the boundary. So if you have two reactants that don't react well together, then of course it's going to be a slow reaction rate. Example might be trying to light fire to water or trying to light wet wood. The nature of the wood, it's wet, it's not going to react very fast. Dry wood, different matter, especially if you have small pieces of it. So, second, concentration. Now, on this one, I want you to know that if you increase concentration, you increase collisions, which increases reaction rate. Larger surface area, which is the same as smaller particle size. We talked about this in the last chapter. If you have a big chunk, like a big piece of firewood, then you don't have very much surface area. The part inside you can't get to because it's surrounded by wood. If we chop it into little pieces, now it burns quicker because you could get all around each of the little pieces, and then it gives you a lot more surface area. Small particles is the same as large surface area, and small particles increase reaction rate. Temperature, you increase temperature, you're going to make things go faster, and that's going to make you have a faster reaction rate because you have more collisions. Catalysts increase reaction rate by lowering the activation energy hump. If you had a long, tall wall to climb, that will take you a while. But if you make a short wall, well then you go right over. It's quicker. That's what catalysts do. They lower the activation energy required, thus making the reaction go quicker. They generally do this by having an active site where they lock in the reactants, and it makes them be right next to each other. They react quickly, and then it dumps them out and grabs two more, and it keeps going. Catalysts are not used up in a reaction. It's like a tool in your toolbox. You use it over and over and over and over, and the parts go away, or you sell them, or you use them, but the wrenches and the tools stay there. They're not used up. Inhibitors, kind of the opposite of catalysts. They inhibit or slow a reaction, or they may kill a reaction. And they could do this by affecting the reaction, or they could actually affect the catalyst and make it inactive so it doesn't speed the reaction up anymore. So again, how do catalysts work? This diagram shows you real clearly. Uncatalyzed is the red on this diagram, the tall slope, and that means that you have a slow reaction. When we catalyze it, then we have the blue slope, which is the low one, and it's labeled even if you have a black and white diagram, and that's going to be a faster reaction. So faster reaction rate with catalysts because it changes the height of the activation energy. So two types of catalysts. A couple of chapters ago we talked about homogeneous, which means same. If you put a liquid catalyst in liquid reactants, that's homogeneous. If you put a solid catalyst in liquid reactants, that's heterogeneous because it's a different physical state of matter. That finishes the first side. If you flip it over, we're going to go ahead and hit that other set of notes. So you got a little intermission there. Maybe you got time for a little snack or something. So we're going to talk about reaction rate laws. And what a rate law is it is a mathematical statement, basically, or an algebraic statement that helps us understand how fast a reaction goes and how the parts of the reaction, the reactants, affect the reaction rate. Because each reactant may have a different type of effect. Some of them may be what we call first order, and when you double them, they double the reaction rate. Some may be second order, so when we double them, they quadruple the reaction rate. So we're going to look at rate laws, how to write rate laws, and how to determine what the order of a reactant is, which basically tells you what kind of effect it has on the reaction. So all rate laws that you write are going to start out rate equals K. So when you see something that says write a rate law, write that down first. Rate equals K, and then brackets to represent each of the reactants. If you have two reactants, you're going to have two pairs of brackets. If you have one reactant, you're going to have one pair of brackets. And the formula for the reactant, not the coefficient, just the reactant's formula goes inside the brackets. Now the brackets help group just like brackets always do, but they also have another meaning, and that means that the bracket means moles per liter concentration, also aka molarity, capital M, from a couple of chapters ago. So that bracket has that second meaning. The superscript that we put on each bracket comes from the number in front. So the number in front, which is the coefficient, in a balanced equation, that is put as a superscript, and we call that the order. There's one more piece to a rate law, and that is the constant, and it's represented by the letter K. The rate constant is the same for a reaction, no matter what the quantities are, and you can look those up on a chart, or you could actually calculate those. And that rate constant for a reaction is like it says, it's constant, it's the same. So the value of K, we'll talk about how to calculate that in later slides. The overall order of a reaction is equal to all of the orders added together. So if you have two reactants, one of them's second order, one of them's first, the overall order would be third order of reaction. So determining reaction order and the constant from experimental data, the only way you could really determine the rate of a reaction is experimentally. And when we do that, we record the data in charts just like we always do, label the chart real well. We have our units labeled here. And so in this case, we've got two reactants, nitrogen monoxide and hydrogen. And we look at the data, and I've got there's a separate tutorial on how to use initial rate data in order to determine order, and I would recommend that you look at that if you have problems catching it from this quick once-over. We've got one reactant represented on the first video, and then two reactants like we have here that's a little bit more complicated, but not so bad. How do we do this? Well, first of all, you know from the scientific method that you shouldn't change more than one thing in an experiment, because if you do, you're not going to know which thing you changed affects the results. Well, the things here are the reactants. And notice on the column, this is the same chart that you got in your notes, that H2 is held constant for the experiment 1 and 2. In other words, H2 is not a factor. So we cover that. Now basically we have the same thing as one reactant because we're looking at one reactant. And if we notice, the nitrogen monoxide doubles. When it doubles, if it were first order, that would be a power of 1. Then basically that's the identity for exponents. When you have something to the 1, it's not going to change the value. So if we doubled to the first power, that means it's going to double the rate. Now, what if we put 2 in the bracket and put it to the second power? Well, that would be like doubling with second order reactant. And of course, doubling a second order reactant is going to quadruple the rate. So you see how that exponent changes how a reactant causes changes in the reaction rate. And like I said, I've got a couple of videos, one of them that does one column and one of them that does two column data like this. And it would be worth your while to look over those and spend a little bit more time looking at that. But we're going to take a quick look and solve this problem. And then, like I said, if you need to rerun it or you need to go look at those other videos, that'd be my suggestion. So again, we cover the second column because 004 and 004 held constant. That is not going to change the rate. So we go from 0.001 to 0.002, which is doubling. And what I recommend you do on the side is write 1 in brackets and then a 2 in brackets and raise it to the first power and say, well, let's see, 1 to the 1 is 1, 2 to the 1 is 2. So if I had a first order reactant, then it would double the reaction rate. This one quadruples the reaction rate. We know it's not first order. So the next thing we do is we do 1 to the 2 and 2 to the 2. Well, 1 to the 2 is 1. 1 times 1 is 1. And 2 times 2 is 4. So what happens when we raise the exponent to the second power is that when you double the reactant amount, it quadruples the rate. So we look at the other reactant. Now we notice that NO is held constant on the last two. So now for experiment 3 and 5, we can cover the first column and we look at the second column here. Notice that the 0.001 to 0.002, again, this doubles, but the rate doubles from 0.008 to 0.016. So when we have a reactant double and the rate doubles, well, you know that already, that when the same thing happens, then it's first order, because raising something to first power makes it the same answer as, or the same result as what happened inside the brackets. So we now know that the NO is second order and that the H2 is first order. Now we can actually write the rate law for that. And the way you would write that, remember how we start all rate laws? Rate equals K. So rate equals K, and then we put brackets. And how many brackets? Well, we've got two reactants, so we're going to put two sets of brackets. Remember, the brackets mean mole per liter also. So we've got two ingredients here. We have NO and we have H2. Okay, now we decided that NO, when it doubles, it quadruples, which is a second order. And when the H2, when it doubles, it causes the rate to just double. So doubling and doubling means that we have something to the first power because it doesn't make a different rate effect than our change in the quantity. And this is probably one of the hardest things in this chapter. If you catch it from what we just talked about, great. If you need more help, remember those other videos. So now we have this. Let's say that I wanted you to solve for the rate constant now. Well, we have the rate because we have that on our chart. It tells us that in experiment 1, the initial rate was 0.002. So we plug in 0.002 for the rate. And that's molarity per second. We know the concentration of NO because it tells us it's 0.001. And we know the concentration of H2 because it tells us it's 0.004. Well, now we've got everything in our equation except for the K. So what we do is you can divide both sides by our two sets of brackets, or you do the Anderson swap and you swap those down. We talked about both ways to do that in my classes. So if we divide both by 0.001 squared and 0.004 to the 1, we end up with 0.001 in brackets squared on the bottom and 0.004 over here. And of course, identity, anything over itself is going to equal 1. And now we have a problem where we've got 0.002 divided by 0.001. Don't forget to square it. And also divided by 0.004. That equals the value of K. That's how you solve for a constant given data from at least one experiment. You may not be given a chart. You may be just given the data from one experiment. Now we know the K value. Then we could come back if we know K and we know new data for these, we could solve what the rate's going to be. That's the main purpose of a rate law, is to tell us how fast a reaction is going to go based upon the rate law and the data that we plug in. So again, if you know the NO and you know the H2 and you know the K, we could solve for rate. So it's very flexible, just like any other algebraic equation. You could plug in, and if you know all the pieces of information but one, you solve for the unknown piece of information. Reaction rates and mechanisms. So there's two ways we can find instantaneous reaction rate, and we just went over one of them, and that is to actually have the rate law and plug in the K value, the reactant 1 and the reactant 2, and solve for the actual rate. And that gives you the rate at any one time, called the instantaneous reaction rate. The other way is that you could get experimental data, and from the experimental data, you could actually graph and make a curve. And then, you know, the final piece of information that you need in order to calculate the instantaneous rate. So we're going to draw a curve here. And this would be moles in seconds. And the way you take a curve and you find out instantaneous, let's say we had at 3 seconds here, we're just going to pick a time. At 3 seconds, we're going to go up to this point right here, and we're going to make a tangent line at that point. The slope of that tangent line tells us the reaction rate at that exact moment, at that instant. So how do we figure out the slope? Well, you've done that in math many a time. You know that slope is rise over run, so we need to figure out how big the rise is and figure out how big the run is. And you could do that a number of ways, but once you determine that, the rise over run, you actually have the slope. Now, how do you know what the slope represents? Well, it's always rise, which would be molarity in units, over seconds. And that's molarity per second. That tells us what it is we're solving for. What we're solving for there is molarity per second. You know that to be reaction rate. So if you're ever asked, what does the slope represent? Well, circle the units in the y and circle the units in the x, and then look at the units, and it can tell you what it is that we actually are representing. Now, reaction mechanisms can either be a diagram like this, or they can actually be a reaction that are a series of reactions that we summate. In this, I'd like for you to be able to look at it and say, well, let's see. I know it's a complex reaction because I have more than one hump on the diagram. There are 3 humps. That means there's 3 elementary reactions. The middle hump is the tallest on the leading edge, so it's the slowest. The first hump is the fastest because that would be the easiest one to run over if you were running over these hills. So the shortest front edge is the fastest, the tallest is the slowest. Labeling the parts. Of course, reactants will be all the way on the left, products all the way on the right. Each of these in-between gaps are called intermediates because they are products that are formed temporarily by one of the elementary reactions. Here's another set of intermediates. Activated complex, and of course, if we were going to label the activated energy, it would be the height from the leading edge base to the peak. That difference in energy is the activation energy. So you should be able to draw reaction mechanisms if you're given elementary reactions. It tells you they're fast, slow. It tells you that the overall reaction is spontaneous. You know the products are lower. If it's not spontaneous, the products are higher. So also always label your graphs. Reaction mechanism would be my title here, energy on the y and time on the x. Finally, we'll look at summating or summing a reaction mechanism, and we have 2 elementary reactions here. And the whole deal here is you're just adding up. It's like addition. Everything on the left is going to be on the left on the bottom. Everything on the right of the arrow is going to be on the right on the bottom. The only exception here, oxygen O was produced and then oxygen was used. That's like making 3 dozen cookies and eating a dozen. You only end up with 2 dozen at the end. So if you make something and eat it up right away, it goes away. And notice we don't have O by itself in that reaction. Now remember, O2, O3, O, they are all different. It has to be exactly the same to be used up. So it's like a unicycle has 1 wheel, bicycle has 2 wheels. They are different. You can't take a unicycle and a bicycle and call it a tricycle with 3. Okay, so keep in mind when you summate these, they have to look exactly the same. That is chapter 16 in a nutshell, pretty big nutshell here. We covered this all in one stretch. But remember, there are some little sub-videos that cover each of the topics. Hopefully you'll be able to look over those if you need some more help with individual topics like writing rate laws, looking at initial rate data charts, and figuring out the order of the reaction, writing rate laws from that, also calculating K. Study, work hard on your review, do some of the extra tutorials, and good luck.